But I think we have 9 to 12 both days. Yeah, study this weekend. Study this weekend as much as you can. Get into that, dig into that final review outline, so that you make the most out of those review sessions. Okay.
Where can we find that stuff on Blackboard? Will be an announcement?
Yeah, I'll make an announcement. But 9 to 12 both days, Monday and Tuesday. So locations, look for announcement on Blackboard. Other questions? Okay, so let's put it all together here. So you remember the rocket basketball, right? What kind of graph am I showing on the left here for the rocket basketball? Rate of change, right? So this is the rate of change. And what was our, originally, what did we say? We know how fast something is changing at every moment. In this case, the height of the rocket. We know how fast the height of the rocket is changing at every moment via the rate of change function. And what do we want to know? What are we interested in knowing? What's that? We know how fast the height of the rocket is changing, or its velocity, and we want to know what? How high it is, right? Accumulation. So how high from the ground? How high from the ground it is at any moment. At any moment. Okay, and with a changing rate function, that's not a simple thing, right? It took us a month or even the whole semester to really finally get to the point where we can say, all right, now we can model and know exactly how high it is at every moment. Okay? It took us most of the semester to do this. So let's just take a walk down memory lane here. What did we do first? What did we do first? Approximate rate function, right? We picked off exact rates, and we said, let's let the rate be constant over intervals. And why did we do that? What was the advantage of constant rate of change? Because now we just made the rate function worse, right? This step function is actually not the real rate function. So why did we do that? Yes, sir. What's that? Do what? Right, with constant rate, the math was pretty easy, right? Change in y, or in this case, a change in height was just a rate of change times the change in time. Delta y equals m delta x, right? That was our constant rate of change. The math is pretty simple, and we could build a approximate height function. So here was our on the left was our constant rate function, right? So that was our step function, our approximate rate of change function, the steps. And then from that we built the approximate accumulation function. And the first time we did it a piece at a time. For every linear piece from a constant rate, we made a separate rule, right? And then we said, well, we just want one rule, right? We just want one rule for that approximate accumulation function, or in this case, the height function. And so remember, we worked for a couple weeks then, transitioning from a separate rule for every interval to this bad boy, remember? And this was the one rule version of that piecewise linear function. And then we said, what do we do next? So now we've got the one rule version of the piecewise linear function. Well, we want the real height function. So what was the key to moving to the real height function? What's that? If we make the intervals really small, right? We make the intervals really small, our approximate rate function gets much closer to the real rate function, and then our approximate accumulation function gets really close to the real accumulation function, or the real, in this case, basketball height function. And then as we made our intervals really small, what did this equation become? A as we made the intervals really small. Should be thinking integral, right? Integral. So for a very small interval, our complicated piecewise function became the more streamlined integral function, right? Integral function. And this represented the exact accumulation of height, right? But when we look at that, we think this, right? Or we should. When we look at this, we're thinking this, summing up many bits of change, m delta x, right? All for all the completed intervals, plus the little more for the partial interval. But it's all just a big sum of a bunch of bits of change, each one calculated by m delta x. And so this reminds us of that. We're summing up all the bits of change as x increases through intervals, right? As x increases through the really small intervals. Okay. So that got us the represented the exact accumulation function, a net accumulation, right? Or for in this case, the exact height function. And then we said, well, we really only have that in open form, right? We have this open form expression. It would be really nice to have that in closed form, okay? So then we reverse the process, right? We reverse the process, and in reversing the process, we found, oh, it's pretty easy to get closed form rate functions from accumulation, where it wasn't easy to get a closed form accumulation function. But we could use that in order to help us get closed form accumulation functions. So to get these integral expressions in closed form, we saw that this reverse process, or all those mastery rules, could allow us to do that. Okay, so I've got this rate function here. So let's kind of test our understanding of everything here with some questions. If the rocket is launched from a platform 6.5 meters above the ground, write a function for the height of the rocket t seconds after launch. Here I'm giving you the exact rate function. It's t to the 1.3. T to the 1.3. The exact rate function is t to the 1.3. I want you to write a function for the height of the rocket t seconds after launch. Go. See what we can do on this. Okay, we're going to come around and see how we're doing on this. We can work together. We want a function for the height of the rocket t seconds after launch. If I have the exact rate of change function. Oh yeah, you know you got it right. You got it right. So I said t second. This is for
Yeah.
I said t second. Then that would be but for b you'd have this one.
Not
Actually, the only thing is like 7.
find out what
Find the close one.
because that's what now what the is response there's one in front of you.
Okay, so I want to write the height of the rocket. The height of the rocket. How do I do that? Do I have my list? I got my list. Let's see. Volunteer, height of the rocket. Anybody? Yes, sir. 6.5. 0 to t. Okay, and what is r sub h of x? X. Yeah, so let's use something else besides x. So x, that'd be perfectly fine, but I'm just going to use, say, v. No. U. Just some other symbol besides t. X would be perfectly fine. I just, yeah. So here's one way to write that. So what is it? It's the initial amount of accumulation plus the net accumulation of height, right? The net accumulation of height will be our integral from 0 to t u to the 1.3 du. Because that's our what? Our exact net accumulation starting from 0. And then to get total accumulation, we add whatever, some accumulation that we had before time equals 0. Okay. Can you write it in, so is this open form or closed form?
Okay.
Can you write it in closed form? So can we write it in closed form now? See if you can do it. So we've talked about 2 ways now to express net change, right? 2 ways to express net change. We can express net change by an integral, or what's the other way we can express the net change? What's the other way we can express net change? From Tuesday. That's part of it, but what's the structure of net change? So before we get to that, how do we express a net change other than an integral? Final minus initial, so it'll be, now it won't be h, right? It won't be h. We need something else. So f, so say f of t minus, and what is a? F of t minus f of 0, right? So this is, we know this the other way. And then what's the relationship between f and u to the 1.3? U to the 1.3 is the rate of change of f. So we got to think, okay, I need this. What function, if I took the derivative of it, did the rate of change, would give me u to the 1.3? That's the way I want to think about this. And so when we had power rule and took derivatives, what did we do to the power? We subtracted. So what are we going to do now? We're going to add. If we're going backwards, if we want the function whose derivative is u to the 1.3, it's going to be u to the 2.3. Okay? So it's going to be u to the 2.3. Now, if I took the derivative of that, would I get u to the 1.3? Not quite. So what would I get? I would get 2.3 times u to the, 2.3 times u to the 1.3. A 2.3 that I don't have. So I need to adjust this. How do I adjust it?
You multiply 10 to the 23rd, put 10 to the 23rd in front of the u, because if you multiply 2/3 times 10 to the 23rd, you get 1.
10 to the 23rd. It's 2.3, guys. This is 1.3 and this is 2.3. So yeah, so we're gonna need 1 over 2.3. Right? If I have 1 over 2.3, now I take the derivative of that, I'm gonna get just plain old u to the 1.3. So therefore, that's my antiderivative. So what I'm gonna do, I'm gonna evaluate that at t. So any questions on what I just did? I'm thinking about working on, u to the 1.3 kind of as a mastery problem in reverse. What function would give me u to the 1.3 as its derivative? Well, it's got to have a power 1 greater, but if it had a power 1 greater, I would have this extra 2.3 in front when I took the derivative, which I don't want. So I need 1 over 2.3. Doesn't make sense. Okay? So then I'm going to, what? So now the other way, I've got an antiderivative, and so as an accumulation function, so I can, what? Evaluate it at, to rewrite this integral as net change this way, then I can write it, evaluate it at t, and evaluate it at 0. So it's going to be 1 over 2.3, what? T to the 2.3. And then in this case, f of 0 is 0, but it's not always, okay? Just because you're plugging 0 in doesn't mean you're always going to get 0. In this case, you do. So it's going to be minus 0. So look, we got it in. We got our total accumulation function in closed form, not just open form, given the rate, right? So mission complete. You know how fast something is changing at every moment? You want to know how much you have at every moment? We got it in open form halfway through the semester. Now we can write that in closed form. So what are the units on that function? What's that going to give us? Just plain old meters. Because this is the height of the rocket now, t seconds after launch. Exactly. Any questions on that? Does it make sense? What's the height of the rocket 4 seconds after launch? Piece of cake. Do it. Find it. Represent it first of all, and then find the value. Represent it and find the value. How do I represent it with the notation we've? Yeah. H of 4, right? H of 4 is what we're talking about here. And how do we calculate H of 4? Yeah, so now we got the closed form, right? And we just plug 4 in. Whereas before, what we'd have to put 4 here in this open form and then have some kind of technology do it for us, right? Meaning we can't just quickly punch something in the calculator, right? So what did you get?
17.04.
Someone else get that? All right, look at that. The beauty of a closed form expression. Now I know, and I could do this for any number of seconds after lunch and rapidly get all the different heights, right? We know the height of the rocket at every moment now, and we know it quickly. Cool. Okay, one more question. Express and calculate the change in height of the rocket from 2 to 5 seconds after launch. Express and calculate the change in height of the rocket from 2 to 5 seconds after launch. Let's see. Let's express it in 2 different ways. Express it in 2 different ways. Yeah. Right. You don't want to use h there. H is 6.5 plus the integral. Yeah, yeah. All right, what's one way to express the change in height from 2 to 5 seconds after lunch? Somebody knew. What's one way to express the change in height from 2 to 5? Somebody knew. How about right here? Tell me your name. Yeah. Sean. He wants h of 5 minus h of 2. You like it? Okay. So then what's another way to express that? H of 5 minus h of 2. Another way to express this. Yeah.
The integral from 2 to 5 of r of x or r of t. U.
Yeah, so we'll do it easy again. What do you think? Does that get the change in the height of the rocket starting at 2, ending at 5? Yeah. Is this a function, a value, or something else? What is that whole thing there? Is that a function? Or is it a value? Or is it something else? It reflects a process, but what? It's just a number, right? It's just a number. Even though the rate of change is in terms of u, we're going to accumulate starting at 2, ending at 5, at that rate, at that changing rate, and then we're going to get an amount of accumulation. Anybody have it? What is it? 15.47 meters? 21.97. $21.97.
You don't have the 6.5.
Okay, but now let's think about this. The change in height from 2 to 5 seconds, does it have to do with the 6.5 meters? No, it doesn't. It would be the same change in height if we started 10 meters above the ground, or 1 meter above the ground, or on the ground, right? The change in height from 2 to 5 will not. And what will happen when you do h of 5? How is that shown? When you do h of 5 minus h of 2, what will happen? You'll subtract them out, right? H of 5 will have 6.5 added, and h of 2 will have 6.5 added, and that'll subtract, those will cancel out. That's why the integral that has nothing to do with the 6.5, okay? So it doesn't matter what we initially start the rocket at. The change from 2 seconds to 5 seconds is irregardless of that. And you'll see that will get, so then if that's the case, what is that the wrong answer? It is 15.47, okay. So you just don't tack on 6.5, because that change from 2 to 5 doesn't matter that you started at 6.5 or 10 or 2 meters above the ground. So that 6.5 goes away when you subtract 2 different values of h, and then you see no 6.5 in that integral. Okay, questions on this? Okay. So it should feel good, right? We had this journey all semester long with this question in mind and this pursuit in mind, and now we've arrived, okay? And we used, lots. These questions are involving maybe 70-80% of what we worked on all semester. So really what we've been working on this week and all semester is the fundamental theorem of calculus, okay? The fundamental theorem of calculus. The net change of an amount or total accumulation, modeled by F as X changes from A to B can be represented in two ways. We can do final value of F minus initial, or we can do the accumulation of many changes of F, each one computed by M times dx. So, what is final value minus initial? That's just F of B minus F of A. And then the accumulation of many changes, each one computed by M dx, is what? That's our integral from A to B of the rate of F, right? The rate of F, t dt. So because they're both computing the net change, they're equal. Okay? And then if we let B vary, if we let that endpoint vary, then we have a net accumulation function or a net change function, right? Net change function, again, expressed in two ways. Using the total amount function, F, using integral in the rate function. Okay, and remember we talked about last time? So if our lower limit of integration is A, then we have a reset. So that the net accumulation value, I should say net, on the wrong screen. I'm on the right screen now. So this is the net accumulation. Come on. I just showed that it worked. Anyway, let's just say net accumulation. Okay, so the net accumulation value equals 0 at x equals A. All right? But the total accumulation at x equals A doesn't necessarily equal 0. That's f of A, right? So f of A would be whatever our total accumulation is. That doesn't necessarily have to be 0. But so that net accumulation is 0, we subtract that off, right? So in order to get net accumulation to be 0, we need to subtract off the total accumulation at x equals A. And then we have a net change function. Should make sense. Okay, so this is a very important statement that we've been working on understanding, developing and understanding. Okay, and that is essentially the statement of the fundamental theorem, that if capital F is any antiderivative of little f, then this integral expression, integral from a to x f t dt equals what? Finish it. Write it down. Finish it. You're all taking notes, right? What does it equal? How about in the light blue tank top and glasses? What is it equal? Which f? Yep. Yeah, the big one or the small f? Big F of x minus big F of A, right? Okay, and so then if you can use that function, but you can isolate a particular value of x, and then you get amounts of net change, right? So a to b, the integral from a to b equals f of b minus f of a. This now gives you a particular value of that function, right? A particular value. You're picking a b, or you're picking a value of x to which you want to accumulate. And so now we're getting a particular value. Okay, so this property has enabled generations of people to do calculus exercises without understanding calculus. But you guys are way ahead of that. You're way ahead of the game because you know in detail what's going on here and what everything means. Okay? So let's talk about this. So f of x equals e to the cosine x. If we thought about that as a rate of change function, does f have an antiderivative? Does f have an antiderivative? What do you think it is? We'll call it capital F. E to the cosine x? 1 over cosine x, e to the cosine x? What's going on? How's my pen working? So test it. So come up, think whatever you think the antiderivative is. Test out your conjecture. Test out your conjecture. So I heard a couple possibilities. I heard e to the cosine x as one possibility. All right, capital G. Another possibility, 1 over cosine x, e to the cosine x. Any other possibilities? 1 over sine x, e to the cosine x. Over negative sine x, e to the cosine x. Do any of these have as its derivative e to the cosine x? So let's capital F. Is that derivative e to the cosine x? No, it doesn't work, right? Because the derivative would be e to the cosine x, so the derivative times negative sine x. So this is no good. Doesn't work, right? What about this? No. Okay, so what about this one? Is the derivative of this little f? Does it work? No way. Why not? We got e to the cosine x over negative sine x. What's the structure of that? Quotient rule, right? Quotient rule is going to blow up. It's going to be nothing like this because this is quotient rule now. You can't do that trick unless it's a constant, okay? You can't just divide by 1 over that thing. If it's a function, well, that changes the whole ballgame. Now we've got a quotient. Quotient rule will be nothing. Be this kind of complicated fraction that's not e to the cosine x. Okay? So, what we're finding is that e to the cosine x, does not have a closed form antiderivative. It doesn't have a closed form antiderivative, meaning there's no elementary function or basic function whose derivative is e to the cosine x. Does that mean it doesn't have an antiderivative?
No.
Okay, so how can you express an antiderivative of that even though it doesn't have a closed form antiderivative? Could you express an antiderivative of that even though it doesn't have a closed form antiderivative? So here is that function. Think of it as a rate function. Is there an accumulation function or functions that are associated with that rate function? How can we express it? If it is, then it's an antiderivative. How can we express it? I heard someone say it. All right, I think that takes me back to my So what do we think? How could I write an antiderivative of this? Meaning, is there an accumulation function whose rate is e to the cosine x? What would it be like? Yeah. Uh-huh. Okay, a to... So let's pick an a. So let's just get one, all right? So let's pick an a. So we'll pick 1, okay? But function. We want a function, right? So 1 to x, right? Sure. Is this an antiderivative of e to the cosine x? Is this an antiderivative of e to the cosine x? Let's graph it. So here's the accumulation function that has e to the cosine x as its rate of change. It's just that there's no closed form version of it. Okay, there's no closed form version of it, but it is an antiderivative. If it's an antiderivative, how can we prove that it's an antiderivative? Exactly. So how can we check that 1 to x e to the cosine b db is an antiderivative of e to the cosine x? We're going to take the derivative of it. Take its derivative. And when we take its derivative, what should we get? E to the cosine v. That will prove, if the derivative of this is e to the cosine v, that will prove that this is a valid antiderivative, even though it's not in a closed form. Okay? So we'll let capital F of x be this antiderivative that we can't write in closed form, but we need something to represent it, so we'll represent it with f of x. Okay, and what we're going to do, we're going to take the derivative of that function. So if capital F is the antiderivative, then what can I do? If capital F is the antiderivative, how can I take the next step? What would it be? d dx of what? So d dx of what? I'm trying to rewrite this integral now. I'm trying to rewrite the integral. Right here. Next to Ivy. What's your name again? Was it? Bailey. I'm going to take the derivative of what? How can I rewrite this integral if capital F is an antiderivative of e to the cosine x? So I want to rewrite this, right? How can I rewrite that? Well, not closed form, but I know that I'm saying I'm letting f of x be the antiderivative. So it won't be closed form, but I can use capital F to do it. What will it be? Go ahead, Ian.
It's capital F of x minus capital F.
Right. It's the same. This is the fundamental theorem, right? So that we're taking the derivative of. So now we're going to rewrite that integral in the what? Net change form, the final minus initial form. Okay? And then if f of x is an antiderivative of e to the cosine x, what's its derivative? So what's d of f of x dx? So again, f is the antiderivative of e to the cosine x, and I'm taking the derivative of it. So what does that equal? E to the cosine x, and now I'm taking the derivative of f of 1. What will that be? That will be 0, right? That's a constant. Got it. So that verifies that that function, integral 1 to x, e to the cosine b, dv, is a valid antiderivative of cosine x, or e to the cosine x, even though e to the cosine x doesn't have a closed form, right? It doesn't have a closed form antiderivative. That's still a valid antiderivative because we just showed its derivative is the original function, the rate function, e to the cosine x. Okay. Does it make sense? So really forcing ourselves to make meaning of the symbols, right? So these problems are good because you really have to know what the symbols mean in order to solve them. So we're going to do some more of these. How about this? So we think, what does it mean? What does this mean? Take a minute, see if you can do it. And actually, this one is a little bit different than the last one. If you recognize the difference, you can reason this out a lot faster, reason out the answer a lot faster. So we're taking the derivative of what? What are we taking the derivative of? An amount of net change, right? An amount of net change from 4 to 7 at this particular rate, sine of 3 cosine x. So when I talk about the amount of change, or the net change from 4 to 7 at this rate, what am I talking about? A value, right? A value. That whole integral is just a number. So when you take the derivative of it, you get? 0. The whole thing is 0 because that amount of net change is a fixed value because we have a known starting and ending point. It's not a function. So we're taking the derivative of a constant, which is 0. So this is more like the last example. So see if you can work through the last example. So this as a hint. So we're going to start by saying let capital F be an antiderivative of sine of 3 cosine x. Again, this is another one that does not have a closed form antiderivative, or not a simple one. Sine of 3 cosine x doesn't have a simple closed form antiderivative, but we know it does have an antiderivative. We just showed it in the last example. So we can let it be f. Let it be capital F. Okay. And now that we know that it's f, now we can make some progress on this. See if you can do it. See if you can do it. Work through all the steps. Don't just write down the answer because the steps are going to be important on harder examples. You're going to need the process on harder examples. So is the integral, is it a value or a function or something else?
It's a function
Ian wants it to be a function. Why?
because it says it doesn't have a specific and
Okay.
add both, then it will be a value. But since it has a start, not an end, then it's a function.
Yeah, so we have a reset at 4, and then we're going to make it a function of where we stop accumulating, right? Where we stop accumulating. Okay, so this is going to be a function. And what kind of function is it? Just the integral part? What kind of function is that? Net accumulation, right? Net accumulation, the change from 4, right? The amount of change we get starting from x equals 4. Okay? And so how can I rewrite that integral? How can I rewrite that integral? As? Yeah.
ddx sine 3 cosine x minus ddx sine 3 cosine 4.
Okay, but is that function its own antiderivative? You just rewrote the function. So that's the rate function, right? So if we're going to write it as final minus initial, it has to be the antiderivative, not the rate function, right? You see? So what's our antiderivative? What I wrote. Capital F. We're saying so it doesn't have a closed form antiderivative, but we're going to let f be that whatever that antiderivative is. So how can we rewrite the integral? Yes, sir. Right. The derivative of capital F of x minus, I guess, yeah, so there should be 4's there where the a's are. Okay? Which means we know the difference rule is derivative of each one, right? The derivative of the first minus the derivative of the second. What's the derivative of f of x? Right, because capital F is the antiderivative, so the derivative of it is sine of 3 cosine. And what's going to be the derivative of f of 4? 0. Okay? So it's kind of showing that this integral expression is an antiderivative of sine 3 cosine x. Okay, harder one. So let's just pick something else this time. So let's let g, this time let's let g of x be an antiderivative of what? Square root of 1 plus x squared. Again, this one does have a closed form antiderivative, but not within our grasp right now. Okay, so that's actually for a topic for Calc 2. But with the rules we know right now, we cannot get to a closed form antiderivative of this. So we're still stuck with this, just representing it as capital G. Okay, so we're going to let capital G be the antiderivative of square root of 1 plus x squared, and I want to make sense of this expression. Here's where working through the steps is going to be important. Okay, so we've got to work through the steps now. Can't just write down the answer on this one. So it's the same as taking the derivative of what? G of e to the 4x minus. The fundamental theorem says there's two ways to express an amount of net change. As an integral and as final minus initial of the amount function, right? As an integral in terms of the rate function and as a final minus initial of your amount function. And so now I'm rewriting that integral as final minus initial net change. Okay, so now we're going to have the derivative of the first. Derivative of a difference is just the difference of the derivatives. That derivative is, this one's 0, it's a constant. And so now we have the derivative of g of e to the 4x. What's that going to be? What is g of e to the 4x? Okay, so it's what? It's the antiderivative So now I'm differentiating, right? I'm differentiating this. So I'm going to get square root of 1 plus e to the 4x squared. Is that it? Look, I'm taking the derivative of what kind of function is that now? This is a composite function, right? So when I take the derivative of a composite function, what do I need? Chain rule, right? I'm going to have to use the chain rule. So yes, the antiderivative is going to be 1 over e to the 4x squared, but I'm taking the derivative, so I need times the rate of change of the interior function. Did you catch it? This is not just g to the x, or g of x. It's g of another function, meaning this is a composite function. And when you take the derivative of a composite function by the chain rule, you need to include the derivative of the interior. So the derivative of this function is this whole thing. Any questions? Did you catch it? Please.
Will there be situations where the a will be the variable and the x will be known? Maybe like a negative number?
Yeah, so like this is a constant up here and this is variable. Yeah, so that would be like accumulating what? That'd be like accumulating up to a fixed value. So yeah, you could do that. Just follow all the same process, but now we're thinking about kind of it's the net change from a variable starting point to a fixed endpoint. Yep, but yep, all the math in terms of the mechanics just follow the same rules, and you can still evaluate them the same. Okay, so let's shift gears here. Any questions on what we've done so far? Yes, please.
I just don't really understand what we're doing. So we're trying to find the rate of change
Yep.
of a function for which we already have the rate of change.
Yes, but this ending is not just plain x. Yes, right. So it's this is an accumulation function expressed in open form. Okay, so that's what the integral is. So this is an accumulation function expressed in open form, but it's kind of a weird one because the end where we're going to stop accumulating is itself a function of x. Okay, so that's what's making this one a little bit different. So the rate of change is not just simply 1 plus square root of 1 plus x squared. Why? Because of this ending where you're stopping accumulating is itself a function, not just x. That's what makes the difference. Did that answer it?
Yeah.
Okay. But yes, we're taking the derivative of an accumulation function which is expressed in open form. And that's going to be what? That's just going to be the rate of change of that accumulation function. Yep, in general. But then you got to watch out for these weird circumstances like this, which allows you not just to write down the 1 plus x squared. Radical. Okay, other questions? Good question. Okay, so let's change gears a little bit here. Let's talk about an alternative understanding of integrals. So we've worked hard on integrals, meaning net change, right? Net change or net accumulation. So let's talk about alternative understanding. And so here's our understanding. We've got a rate function. I've approximated it, and this time using a mid rather than a left situation. So I've approximated it with constant rates. And we've seen that to get this amount of net accumulation, say at 4.2, it would mean adding up these bits of accumulation. The first rate times its change in x. The second rate times its change in x, etc. So this is our familiar way that we've been working on it. So that total accumulation, or net accumulation at 4.2, is the sum of all these bits of accumulation. This is an approximate, using an approximate approach. Okay, so here's a different way to think of this. That R1 delta x, we can see that if delta x is the width, R1, since it's a function value, it's a function value of a rate function, is a y-coordinate or a height. So R1 delta x is analogous to what? Base times height. Base delta x, height being the rate. And that's the area of a rectangle, right? That's the area of a rectangle. And so all of these, so R2 delta x is the height of that second, or the area of that second rectangle. R3 delta x is the height of that third rectangle, etc. Okay? So what we're seeing here as when you sum up these R1 delta x's, we know that is summing up bits of change to get a total net change. But it could also be the idea of summing up these rectangles, summing up the areas of these rectangles. It's the same calculation, okay? It's the same calculation. But this is just the only way, the reason this works out is because we graph in rectangular coordinates. Because our x and our y are perpendicular and everything's right, like a checkerboard, okay, in our rectangular coordinates. So that integration is remotely related to areas of rectangles. It's just an artifact of how we graph, It's just kind of incidental, right? It's just the way that it works out. Okay, so it's not a deep thing, right? It's not a deep mathematical principle like accumulation and rate of change that we've been working on, okay? All right, but that being said, and this goes back to the first day of class when we talked about how this class is different. By and large, calculus has been hijacked by this idea that integration is about areas of rectangles and summing up areas of rectangles rather than summing up bits of change, okay? And so in most traditional calculus courses, that's the meaning that you get for integral is sum of rectangles, sum of thin rectangles, okay? But that, like I said, that's just what's happened. That was an evolution over time. The real meaning behind calculus is accumulation, and that this calculation, R delta x, is a little bit of accumulation that we add, and we add up the little bits to get a whole net amount of accumulation. Okay? So then what happens when we make smaller intervals? Smaller intervals in this area perspective is we get thinner rectangles. More of them. More thinner rectangles for each r times delta x. And the thinner you make them, what does the total sum approach? So for super thin rectangles, like super small intervals, then the sum of all those areas approaches a total area there under the curve to the x-axis. But we just want to emphasize that that's a superficial understanding, right? It's because it has nothing to do with rate of change. If there's applications of it, it's useful, but it's not the main meaning for integral, okay? Our main meaning is our net change. Okay, so let's summarize that. So if the function f is a rate of change function, this is what we've been working on all semester long, then what does this expression represent? From the integral from a to x f of t dt. It represents what? Net accumulation with a reset at a, right, at the rate little f. It's the net accumulation of a quantity with a rate f and a reset at x equals a. Okay? In other words, it's that y value on the net accumulation function, right? It's the y value. Okay? If f is any function displayed in rectangular coordinates, so now it's like what we thought of as the rate function before, but it doesn't have to be a rate function, then this same value we can think about as the sum of all these really skinny rectangles, and we get an accumulated amount of area, the area between f and the x-axis starting from x equals a. So that blue shaded region. The area of that blue shaded region then is an alternative meaning for the value of that integral, the integral from a to x f of t dt. And so little f is like the rate function before, but it doesn't have to be a rate function anymore because you're talking about area, you're talking about geometry. Okay, so let's practice. So here's them both summarized again. Okay, so f is a rate of change function, then our integral is net accumulation. If f is any function displayed, then you can think of that integral as the area of the blue region. Okay, so here's this function g of x. There's the rule for it. And I want to make meaning of this. So what would the geometric meaning now? So we could talk about that in terms of accumulation, but in terms of geometry and area, what would this be? The integral from negative 0.5 to 4 of g of x dx. What would that be? Okay, so we can make a sketch like this. Here's negative 0.5. And here's 4. So what is that integral going to calculate in terms of these shaded regions? So in order to answer this question, we're going to go back and think about this in terms of rate of change and accumulation. So what kind of function, in that perspective, what kind of function is g? Rate of change, right? If it's an integral of it's a rate of change function if it's inside an integral, right? It's a rate of change function. Okay? And I'm graphing g here. So tell me what the accumulation is doing now. What's the accumulation doing right now for these x values? Decreasing accumulation, right? This is g. This is the function g. So the accumulation is decreasing here.
It's still increasing with the rate at which it's increasing.
Good. This is increasing accumulation. This is from your exam last night, right? This is increasing accumulation. Why? G is positive. G is positive, right? Okay. Then down here. Now what's the accumulation doing? Decreasing because g is negative. So what's the contribution of these x values, of the rate function for these x values to this integral? Negative, right? So because g is negative, when we go for those x values, the contribution to that total net change is going to be negative. Accumulation is going down. And then, back when we get to here, accumulation starts going back up again. So in the perspective of accumulation and rate of change, this total amount of net accumulation is going to be an increase, and then a decrease in accumulation, and then an increase again. And we're going to get the change. And the fact that it decreases when the rate is negative is just built into that expression, right? It's just built in naturally. So when we make the transition to area, we have to, it's going to be the same thing. What's going to happen? So the accumulation of area through here is going to be positive or negative? Positive. But when we get to the blue section, the contribution will be negative. Even though we're talking about area, all through here, the contribution to that integral is going to be negative, and then positive again. So if we thought about if I called this A1, and this A2, and this A3. So areas themselves are positive. So A2 is a positive value. It's the size of that region, okay? They're all three positive values. How would I write this expression in terms of A1, A2, and A3? Could you do it? So could you use A1 and A2 and A3 to write an expression that's equal to this integral? What would it be? A1 plus A2 plus A3. A1 minus A2 minus A3, or plus A3. So which is it?
A1 minus A2 plus A3.
So if A2 is a positive area, areas are always positive. So there's that positive region there. But the integral is going to, what? It's going to subtract out all that area because G is negative there. So this integral, so those who said minus, got it. So that integral would calculate A1 minus A2 plus A3. And that's what that integral will calculate. Okay, does that make sense? So what if I want the total area? I want to find the total area bounded by these graphs using the function g. We got to figure out how to do it. How to find the total area bounded by the graph of g. So in other words, what is A1? Again, A1 here, A2, A3. What is A1 plus A2 plus A3? I want to write that in terms of g. How can I write an expression in terms of g that will give me the sum of those three positive areas? See if you can do it. Okay, and here's a hint. We'll call that point x1 and that point, other point x2. That's a hint. Keep working on it. Anyone think they got an expression that will do it? Yes, yes, sir.
The integral from negative 0.5 to 4, where the rule is the absolute value of gx dc.
He wants this. Will it work? What will happen? So, as x comes along like this, what will happen to the absolute value of g of x? What will it be? Same as g of x, right? And then when we come through these x values, is it? It's going to take all those negative values and make them positive. So in effect, it'll be like this. The mirror image, right? And then back to after x2, the same. So then it'll be that plus that plus that. Does it work? It does work. Now, what about evaluating that? In order to evaluate that, well, some parts of the function are the same, and some parts of the function get flipped. So we need a way of thinking about that, another way of writing this that we can actually evaluate using the fundamental theorem. Because this is we can't evaluate this directly in one calculation, because this is telling us that sometimes g of x is going to be g of x, and sometimes it's going to be the opposite. So is there another way to write this that will get us that total area? A way that we could evaluate? Yes, sir?
Can you write it as
Okay, 3 different integrals. Go ahead.
So the integral from negative 0.5 to x1.
Okay. Yep. Yeah. Is that what you're going to say? Yeah. All right. So if we break it up, then we want just the plain old integral from negative 0.5 to x1 to get that first red region. But if we want the area between x1 and x2, the actual area, what do we have to do? We take the opposite of the integral. Because the integral is going to give us a negative value, a decrease of accumulation, right? So it's going to give us a negative value. But if we take the opposite of it, we'll get the positive. And then just from x2 on, just the plain old integral. So then the expression would be this. The total area then is wherever the function is negative, we have to subtract off that integral. And that makes it positive. Now, evaluating this in the context of area is the same way we evaluated them before. We need an antiderivative, and we're going to use the fundamental theorem, right? So if you could write an antiderivative of g of x, then it would be that antiderivative evaluated at 4 minus that antiderivative evaluated at x2. So even though you're in the area perspective, evaluating integrals is exactly the same. Use the fundamental theorem. Okay. There's one more topic that you're going to need for the web work, to get through the web work and the final exam. So it'll be 15, 20-minute video that I'll post on Blackboard, and you'll watch that. That'll help you get through all the rest of the web work. And then I'll post the locations of the review sessions Monday and Tuesday. Yes, sir.
Hey, thanks a lot for your class.
You're welcome.
Learned a lot.
Great having you. I think you did pretty well in the exam. 24 or 28 or something.
Yeah, I kind of stumbled on that last one, and I really sat there and kind of picked at it for a while. And
No, that's a
changed
good
my
score.
answers around,
Yeah,
so.
that's a good score on that exam. So you did well.
Cool.
Right.
You'll post those later today or tomorrow?
If I would like to today if I have time, but for sure by tomorrow.
Okay, I'll
Yep.
see you around.
Okay.
I'll be taking Calc 2 and 3 soon.
Okay, very good. Very good.
I was going to ask for that. I'm wondering if you could break this into this tomorrow.
What's that?
I'm one of the people.
Okay, sure.
Don't make a point about it. It doesn't say what field they get.
Yeah, I'm gonna reply to everyone individually, but you're gonna go to Jennifer Bonnie's office hours. You know where she is? She's in
Yeah.
ECH also,
Okay.
like right down the hall from me.
Right. Okay.
So what time will you be there?
I was planning 10.
10.
Like,
Are you starting at 10 too, Alexis? Yeah. So you guys will go at the same place.
Okay. Perfect. All right. Thanks.
She'll be there to receive you.
I asked Morgan if I can look over like my past exams, like
Sure,
during
yeah.
the review.
Yeah. We'll accommodate you guys for that. Definitely.
Tomorrow at 9 o'clock, they had made a reschedule. Is that still?
9 a.m.
Yes.
Yep.
Or
It's Jennifer Bonnie's office hours.
okay.
You know, do you know her? Or ever been to her office?
I haven't
Friday
read
morning.
it. She's just down the hall.
Right down the hall from me.
Okay.
And the room number is on the office hour schedule.
Okay.
Yep. Perfect. Yes, sir.
For God forbid I didn't test that thing again.
No, I think you did.
I did?
You did.
Okay.
Yeah.
Thank God.
I think you're good.
All right, thanks.
Okay. Sorry. Good job.